just do it. Okay, I started. Okay, so this was the example 6.11. Okay, and earlier we did it in the class. So now today we will write the script for this in MATLAB. Remember that the purpose of writing the script in the MATLAB is to get the detailed step-by-step solutions. Otherwise, using MATLAB or in Excel, we can use the dedicated functions to find the answers very quickly. But it is not the main purpose. The main purpose is to find the detailed step-by-step solutions and how to simulate it, our hand calculations on MATLAB. Okay, so in MATLAB, we will start, then we will, in this, for the script, we will go to the edit window. Okay, so this edit window will open, and now I'm writing the, which one? Fixed point iteration method for the system of nonlinear equations. So the comment, I can write it like this. Fixed point iteration method for the system of nonlinear equations. So this is the script. So we can start from the stopping error. Okay, stopping error, maybe, I don't know, maybe you can take any 0.001. Okay, so this is the stopping error. And then for this script, okay, now I'm doing it with the example. So you have to take some example, okay? So this example was this with the values of x is equal to 1.5 and y is equal to 3.5. Remember that we are going to solve these two equations. X squared plus xy is equal to 10 and y plus 3xy squared is equal to 15. So in the fixed point iteration method, so we can write these equations in terms of like this: x into 10 minus x square over y square. But for in this example, we found that using this type of form, the solution was not converging. So therefore, we will use this form: x is equal to square root of 10 minus xy, and y is equal to square root of 57 minus y over 3x. Okay, and then we will perform the solution. So our starting values are 1.5 and 3.5. Okay, so x is equal to 1.5. Okay, and then y is equal to 3.5. Yeah, I think maybe it's better for me to write like x naught, y naught. Okay, because later on I will find x1, y1. Of course, these are my starting values. And then for this, then what I need to do is I need to find from x naught and y naught. I would need to find the x1, y1. Okay, so from x naught I will find x1. So x1 is equal to sqrt square root 10 minus x naught times y naught. Okay, and then close it. You can see that, for example, yeah, its form is x is equal to 10 square root of 10 minus xy. So we can represent it, and then similarly y naught we can represent it. So y naught is equal to sqrt 57. I think I need to put double bracket for 57 minus y. For 57 minus y naught divided by 3 times x, 3 times x, okay? 3 times x naught, Okay, and then close the bracket. So you can see that 57 minus y over 3x naught. 3 times. So 3 times. For the times, I will put asterisk over here. Okay, and let me see. It is 57 minus y over 3x. Okay, so here I have 57 minus y over 3x. So here we can do it like this as well. Because for this for this evaluation of say it actually should be y1. Okay, for this evaluation of y1, we have this y naught value and then x naught value, but the x naught value has already been updated to x1 in this case over here. So it will be better, although we can do it with x naught as well, but it will be better if we use the updated value. So in this case, the solution may converge rather quickly. Okay, so with it will also work with x naught, but we can also use x1. So that will be much quicker. Okay, so in this case now we have the x naught and x naught and y naught values, and when we have updated it to x1 and y1 values, so we can find the error, absolute error. So, but in this case, because now we have two variables x and y, so we can find the absolute errors in both. Okay, EA, it is the absolute error, absolute relative error. So I will say absolute relative error in x as EAX. Okay, and then I can write it like which will be the absolute value of because we have found from x naught, we have found x1 from x naught, so it will be x1 minus x naught divided by x1 and multiplied by 100, and then bracket close for the absolute, and then put the and similarly for absolute error in y, I can just copy and paste this and then change x with y, x, y, y naught. So this these two lines will give us the absolute relative errors, and these two lines will give me the updated values of x1 and y1. Okay, so this process can be repeated. Okay, that means x1, y1, EAX and EAY can be repeated. So since it can be repeated, then we can put it in a while loop. Okay, while, okay, EAX is greater than ES and EAY is greater than ES, stopping error. Okay, so now look at this over here. Here I am using this double ampersand sign. Even if you can use a single ampersand sign as well, but for if we want to check both of these conditions, EAX is equal to greater than 0 and EAY is greater than ES, EAX is greater than ES and EAY is greater than ES, you should use and. If you will use single and, it will give you some warning, but it will say that for numerical comparisons, you should use a double and. So it will be like the and operator. Okay, that is if you want to search this term, and then if you also want to search this term, you normally put A and D and, okay, in Google search. So in MATLAB, this and is double ampersand signed over here. Okay. So while EAX, that is greater than this stopping error, and while EAY is greater than this stopping error, we will run this loop. Okay, but I think we need to just complete some processes first, because we have not defined EAX and EAY over here. So first of all, we have to define EAX and EAY. So EAX, we can take an arbitrary value of, say, just 100 over here, because this for the start, this 100 will be greater than this ES. And then later on, by after repeated calculations, this EAX will decrease. And then at some point EAX will decrease, then EAS, and then that while loop will stop. So similarly, we can define EAY is equal to 100. This is just arbitrary, okay? Because 100, we know that it's greater than this 0.001, okay? Any value greater than ES will work over here, okay? And then we start from I is equal to 1, okay? That is, this is I is equal to 1, okay? This is for the iteration. And now we need to now we need to also print the values, okay? So the values which I want to print can be written down like this. So this command fprintf will, and then I am putting it before the while loop. That means I just want to print it only one time. Fprintf will print the headings of the table which I want to show, which is the iteration xi, yi, xi plus 1, yi plus 1. So these are the initial estimates, these are the updated estimates, and then EAX and EAY, absolute relative errors in X, absolute relative errors in Y, and then slash backslash N for the next line. Okay, and then colon. So this will, and then from here the while loop will start, and in the while loop these commands will be run. Okay, when these commands will be run, then I will need to print out these values, the answers which I have calculated. So for the printing out of these values, I will put this command. Okay, fprintf. Okay, and then I will put these percent codes over here. And remember that, for example, for the iteration, it is an integer, and for the iteration, it is an integer, then xi, yi, xi plus 1, yi plus 1, eax, eay, and then slash n. Okay, and right. So, but here I think these values in the brackets are important. So how many bracket values? So x naught was already defined here, okay? Y naught was already defined here, and then x1 was found from here, y1 was found from here. Similarly, EAX and EAY were calculated here. Okay, so once these values were printed, will be printed, then we have to update our iterations. So I will be equal to, I will be iterated by 1, I is equal to I plus 1. So that will give us the second iteration value. And then next will be that now the new x naught value. So for example, after that, in the second loop, the new x naught value will be the one which will be previously for x1 value. So we will need to use this x naught value that is equal to x1 previously. And then we will need to use y naught value that was y1 previously. Okay. And then from at here, we will end the loop. Okay. We will end the loop at here. Okay. So with this, I think the code will complete, and then if it is everything has been done correctly, this code will run smoothly. So save it. So I will save it with the name uh, fixed uh, fixed point. Okay, fixed point. Okay, fixed point iteration. Fixed point. Okay, for the nonlinear system. Okay, system, and then I have done it in the for the lab, so that I will like this. Anyway, I will put the name of this file, so it will save it, and then just clear everything, and now I will run this code. Okay, so this means that I have made some error. Okay, so what is that error over here? So it says that the error is unrecognized function or variable y1. And error in fixed point line 11, y1 is equal to s squared, sqrt is equal to this one. So there is some error over here. So I need to fix these errors. So it says that why not here line 1, okay, y1. So y1 is equal to sqrt 57 minus y naught. 57 minus y naught divided by 3 into x1. That was correct. And here, yeah, actually I should put equal sign over here, and I forgot to put equal sign. Yes. Yeah, so this was the mistake. Okay. So now I will run again. And then, yeah, so it seems that now the script works. So in this script, you can see that the values started from 1.5, 3.5, 2.179, 2.86, and then the errors were 31.17 and 22.35. And then gradually the values converge to 2 and 3. So these were the solutions. 2 and 3 were the solutions. Okay, so if you see that from here, in the first iteration, we got 2.179 and 2.86, okay? So 2.179 and 2.86. And in the second iteration, we got values of 1.94 and 3.04. So 1.94 and 3.04. And then similarly, then these values are decreasing, and then we are getting the converged solution at 2 and 3. Okay. So do you have any questions regarding this? Do you have any question regarding this script?
No.
I have a question. The stopping error in the beginning, it's in the percents?
Yes,
Like,
everything, yeah, is in percent, yes. It is 0.001%. Because for the EAS, we are using times 100. So we are taking the values in percent.
Okay, thank you.
So the values, for the first case, the value was 31.17% and 22.35% in X and Y respectively. And then later on the values decreased to points. So for example, here now, if you say, I say choose 1% error, okay? So I can do that, okay? So, so I will run it. If for the 1%, then I think only this much, okay? Iterations will be run. If you, if I want say 0.1, so I can change it to 0.1. Then more iterations will be run. So for 0.1, I think 6 iterations will be needed. Okay, so this was the first script which I wanted to illustrate. The second script is the Newton-Raphson method for the system of nonlinear equations. So the second script. So the second script is from this example. Yeah, so you have this these set of equations. So for example, xi is equal to this and this and this. So for example, in this case, the formulation is like this. So you have the u and x function. So in this case, for the Newton-Raphson method, we will have to define the u and v functions. Okay. So we have to define the u and v functions. And from these u and v functions, we have to take the partial derivatives. For example, partial derivative of u with respect to x, u with respect to y, and then the partial derivative of v with respect to x, v with respect to y. And then we'll input it, and then we can write the script as well. Okay, so let's do this script. So for the new script, then I will just put this with this plus sign, and then I will start writing this script. So stopping error, okay, maybe 0.0001. Okay, this is up to you. Okay, this is the stopping error you have taken, and then we will do the iteration. So the iteration will start from 1. Okay, and then I'm doing the same example, same equation. So initially we took x naught is equal to 1.5 and y naught is equal to 3.5. So I will take x naught is equal to 1.5 and y naught is equal to 3.5. Okay. So x naught is equal to 3.5, y naught is equal to 3.5. And I want to print the table of values. So this is the heading of the table. So which is the same which I can use from the previous example, from the previous script. I can use it. Okay. The next is initial values of EAX is equal to 100. This is just arbitrarily you can choose, because just to start the, I think these values for EAX and EAY we need to start the while loop. Okay. Because otherwise, if we will not define these values EAX and EAY, that is, then the while loop cannot start. So I can start the while same as before, like this. Yeah, while. Okay, so while EAX is greater than ES, EAY is greater than ES, then okay. So for this while loop, so now, so we need we need to because we need to use this two formulas. Okay, so we need to define these variables. So we need the u variable and v variables. Okay, so we will define u naught, v naught. Okay, so we can define u naught, v naught. Okay, so u naught is equal to, but what will see, what is the u naught? So u naught is equal to this equation. Okay, here. Yeah, u naught is equal to x square plus xy minus 10. Okay, x square plus xy minus 10. So u naught is equal to x square minus xy minus 10. Sorry, x square, x is actually x naught because our initial values is x naught. Okay, and it is plus xy, sorry, plus xy, and then plus x naught multiplied by y naught. So remember to this, put this asterisk sign for multiplication and minus 10. So x square, x naught square plus x naught into y naught minus 10. And semicolon. Then v naught. So v naught is this equation. V naught is equal to y plus 3xy square minus 57. Okay. So it is, I forgot again, what is that? Y plus 3xy square, okay? Y plus 3xy square. So y plus 3xy square minus 57. So just this is y was y naught, and then 3 times x times y, and then x was x naught, y was y naught, and then y square minus 57, and then bracket close. Okay, that is u naught, v naught. Okay, so but now we need the partial derivatives as well. Okay, so therefore partial derivative of u with respect to x will be u naught x, or maybe I can just say ux as well, but maybe okay, just u naught x. Okay, u naught x is equal to, because it is now x square, so it will be 2x, so it will be 2 times x naught, and then it is plus xy, so it will be y, okay, plus y naught. Okay, so that will be the partial derivative of u with respect to x. So 2x naught, 2 times x naught plus y naught, and then partial derivative of u with respect to y, so u naught y. So partial derivative of u with respect to y is equal to u naught y. Okay, so it will be, so it is, because it was x square, so x square, that will be 0, plus xy, that will be x, so it will be x naught. Okay, x naught. Okay, and then partial derivative of v with respect to y, so v naught x. So v naught x, so this is with respect to x, so y, that will be 0. Then this is 3xy square. So 3xy square, if I am taking it with respect to x, so it will be 3y square. 3y square. And then, yeah, so it will be 3 times y naught times 3y square. 3 times y naught square. 3 times y square. And then it will be partial derivative of v with respect to y, v naught y is equal to, now in this case v was this y naught, v is equal to y, so it is with respect to y, so it will be 1, and then this is 3xy square, so 3xy square, it will be 3 times 2, 6xy plus 6 times x naught times y naught. Okay, y naught, and then close. So we have now defined these u naught, v naught, ux, uy, vx, vy. So we have defined these values. Okay, so it will be here. I think there is a mistake. I should put asterisk over here. 6 times x naught over here. So the next is we need to apply this formula for the Newton-Raphson, this formula. Okay, so in this formula, this determinant is this denominator value is common. So we can, for ease of our calculation, we can calculate it separately. So what is that determinant? It is ux times vy minus uy times vx. Okay. So, okay, so now I think in order to save time, I can just copy and paste from my solution over here. So ux vy minus uy vx, okay? So this is the denominator. And now we need to find the x1 value. So x1 value will be just based on the value of x naught, okay? So this is x1 is equal to x naught minus this one. And this is the same as this first formula, okay? And now just to save time, I will put y1 over here, this one. So this is the value of the y1. And next is that the next is that we need to calculate the like before EAX and EAY from the, so I can just copy and paste from the previous script. Okay, so just to align it like this. And after that, I need to print these values. So for printing these values, we can just copy and paste from the previous script the same values, I,
So
x naught, y naught. Yes?
I have a question. So when we will submit our lab report, would we the table solution is just the command window that looks like the same as it is right
Yes, so
now?
you will take a screenshot of this, okay? So
Mhm.
for example, you will take a screenshot,
Okay, like
okay?
this
And then you will paste that screenshot into your
solution.
file.
Okay.
And for this, so for the script, you will have, for example, your script will be saved in your computer hard disk. So for example, it will be under this MATLAB. Under the MATLAB, you can find this file, and then you can open that file in your notepad, and then you, from that notepad, you can copy and paste the script into your Word file. Okay.
I also have a question. So basically all of the scripts that we use in the lab, we covered them on the lab sessions. So should we like rewrite all of the scripts, or we can modify the ones that are on Moodle?
Yeah. Okay. So the scripts which I am writing it over here, and you can reuse them in your assignments. Yes. But of course, in the assignment, I think maybe it will be a little bit different, because maybe you will need to change some of the arrangement of these, how to store these values. So therefore, you will need to make some modifications in those scripts.
Yeah, but the bare bone, we can use the ones that we covered during the lab session, yes? Like the structure.
What thing?
I mean, like the overall structures, like the algorithm itself is the same.
Yes. Yes.
So we
Yes.
can just use the modified versions of that.
Yes,
Yes.
you can modify it. Okay. And okay, so the next, so now you have printed it. So now what we need to do is for our next iteration, we need to in this case the update the values. So we have to iterate the I is equal to I plus 1, and then uh, the next time we need to update the value of x naught to x1, and y naught to y1. Okay. Okay, and then that will end the script. Okay, so this will end the script. Then let's try it. Clear, and then, but I think we need to save it. So save. Save it as like Newton-Raphson system of linear equations for lab. Okay, whatever the name. Okay, so, and then run it. So you can see that the script is running, and then it has converged very quickly. You see, within the first 4 iterations, it has provided you the answers. Whereas in the previous case, for this script, it took more iterations. So for example, in this case, in this, if the stopping error is 0.0001, same as in this case, 0.001. So in this case, it will take how many? 13 iterations. Okay, it will take 13 iterations. And then it will take, for the previous case, Newton-Raphson, it just took 4 iterations. So this Newton's method is much quicker than the fixed point iterations. Any questions about this?
No.
All right. Okay. So now we will do the third script, which I said we will do. That will be about the Muller method. Okay, give me 1 minute. I come back. Okay, so let's do this, the third script, which is about the Muller method. So where was the Muller method? So Muller method is in your roots of polynomial. Yeah, Muller's method. Okay. So in the Muller method, you see that we have this type of formulation. Okay. And okay, so, and this was the problem statement. So in this Muller method, what you have, if you remember that we have this polynomial equation. So we find the roots of the polynomial equation. X cubed minus 13x minus 12 was one of the polynomial equations. And we use 3 values, okay, of this function, and then to find the third value, okay. And if you remember that for the Muller method, we also did some Excel example. You can see the lecture as well. Okay, we did that example for the Muller method. Can you see this Excel over here?
Yes.
Yeah,
Yes.
so we started from x0, then x1 and x2. So these were the three initial values. Okay, and then we calculated f0, f1, f2, the functional values with those initial values. Then we calculated these parameters h0, h1, delta naught, delta 1, a, b, c. Okay, and then we found the discriminant x3 minus 1, x3 2, and then like that. Okay, and then we just iterate it, and then we can find the value. So I think since we have now done many times this type of script, the process is almost same. So maybe I can open my already done the Muller script rather than I will type it over here. And then I think it will be easy for you to understand as well. So here I have actually written the script. So as you can see, as always, we start from the stopping error, and then just for the while loop to work, I have assumed the value of EA is equal to 100. Okay, then that is for the, this is for the first iteration, and then x0, x1, and x2 are the initial x values. And then I defined this function handle for this polynomial x cubed minus 13x minus 12. And then in this case, I'm just using a very simple header for the input, although you can input all these intermediate values as well, but I'm just using very simple header for the output. So now I will put the while loop while this absolute error is greater than ES. So first you will calculate the h naught, which is for according to the formula, it is x1 minus x naught. Then we will calculate h1, and then you will calculate d naught. D naught is delta naught. Okay, in the Muller method, delta naught. Okay, so you can calculate the delta naught, delta 1. Okay, so d naught, d1 are delta naught, delta 1, and then from these values you will calculate the value of a, b, and c. So the values of a, b, and c we will find out, and from the values of a, b, and c, once you find out the values of a, b, and c, a, b, and c, then you can find the value of x3, the updated value of the root. Okay, the updated value of the root by this formula. Okay, but in order to apply this formula, we have to make some additional check. Okay, and if you remember, the check is that the this calculated value of the calculated value of this x3 should be closer to x2. Okay, so but because this formula gives us two values of x3, because here it is plus minus over here, so we will get two values of x3. So we will compare these both values of x3 with the x2. Whichever value will be closer, that value will be chosen. Okay, that value will be chosen, and then the process will continue. So therefore, here we have found out the values of A, B, and C. And in order to make our calculations a little bit simplified, we will find a value of the discriminant, that is square root of the discriminant over here. So what is the square root of the discriminant? It is square root of b square minus 4ac. So I call it as d disk, or whatever name you can give it to this. So discriminant is equal to b square minus 4ac. So here I can check the values of, I can find the values of x3. So I will find two values of x3. One value of x3 will be with this plus sign over here, and the other value will be with minus sign over here. So I name these values as x3 or x3a and x3b. So the one with plus will be x3a, the one will be minus, it will be uh, x3b. Okay, here the only difference between this is that like that. So now which value to choose, x3a or x3b? That will depend on the whichever value is closer to x2. So therefore I will use an if statement over here. So if the absolute value of x3 minus x2 is less than absolute value of x3b minus x2, then that means x3 value is equal to x3a. Otherwise, x3 value will be equal to x3b. So this is the simple if statement. And then you will end this if statement. After that, you will calculate the absolute relative error, which will be the comparison of x3 and x2. And then I will print the result. And after printing the result, then we will update the values of I, x0, x1, and x2. So in this case, x0, x1, and x2 values will be updated in sequentially. So that means previously whichever the value was for x1, that will be the value of x0 now. And then previously, whichever the value for x2 was, that will be the value of x1 now. And in this case, the loop will continue until the EA is less than ES. Okay. And do you understand this process? So this script is almost same as the previous one in structure. Only thing is that there is some check on this, the two values of x3, and we have to choose the right value of x3. All right. So then let's see, can we run this? We can run this script now. So first of all, clear it. And now I run the script. And then very quickly it can give us these values. It gives us these values. So which are the same values which we obtained in this question. So from 3.97 to 4, and then 4, and then from the error of 25, and then this. And yeah, 3.974, the errors of 25, and it has converged relatively very quickly. Okay. So in this way, we can apply the Muller's method. So, so this was the Muller's method. So next is the Bairstow's method. But as I said that I will not do it for you. I will later on give this example for the Bairstow's method for you to do for lab number 2. But remember that for the Bairstow method, I have also done it in the class as well. Okay, so you can see the lecture for that, and then you can apply the same concept over here in MATLAB to evaluate it. All right, so that's all for today. So do you have any questions?
No.
Okay. All right then.